Okay, let's learn about rates of reaction. This comes up in chemistry paper 2. A reaction, a chemical reaction, is where reactants turn into products. Okay, so atoms will rearrange themselves, bonds will be broken, and then bonds will be made. Okay, the rate at which reactants turn to products can be increased. Okay, and it's important that we can increase the rate of reaction, particularly within the chemical industry, where we're making molecules that we need to be involved in a variety of different chemical reactions. This is quite an important thing within the chemical industry, that we're able to increase the rate of reaction. Okay. The speed of the reaction is the rate, how quickly the rate is happening in a given time. So rate means how quickly, or the speed in a given time. Okay, how quickly the reaction is happening in a given time. If we were to plot a graph of how quickly this reaction is happening, we could, over time, measure the amount of product made. The more quickly the product is made, the quicker the rate of reaction. So we could plot this on a graph. I'm going to put amount of product made on the side here. Now, the amount of product made at time 0 would be 0 and would gradually increase. There may come a point where it levels off. It's important that we can recognize the different parts of this graph. This initial part of the graph tells us how quickly the rate is at the beginning, and sometimes we're asked to find the initial rate of reaction. And to find that initial rate of reaction, we would work out the gradient of the initial line like that. So initial rate of reaction is the initial steepness. So the steepness, or the gradient of the line, is how we work out the rate of the reaction. Okay, and if we're looking at the initial rate, we're looking at the steepness of the gradient at the first few minutes or seconds of the reaction. What we can see is, as the reaction continues, the steepness of the line decreases. Okay, as the line curves and the steepness decreases, the reaction here is slowing down. As reactants get used up. And this region of the line, where the amount of product remains the same, means that the reaction has now finished. The reaction has finished. For higher paper, if the question says, what is the rate at 5 minutes, for example, then we need to find the gradient of the line at 5 minutes. So we go from 5 minutes and we look at where 5 minutes hits the curve. And we then draw a tangent. And a tangent is a line that touches the point of interest, but the space either side is equal. Okay, so if I just put that on 10 centimeters and I look at 1 centimeter either side, I can see that the amount of space between the curve and the ruler is about the same. Okay, if I go a bit further, maybe I might want to tilt it a little bit like this. That's probably a bit better. Okay, so we draw a tangent to the line if we're looking at the rate at a particular point. This is for higher paper. Okay, and we draw the tangent, and then we do the gradient of that line. Gradient being change in y over change in x. My advice is, when you do a tangent of any description, pick 2 points on the line where you can easily read the coordinates for x and y. Pick 2 points. This isn't on graph paper, but if it was, pick 2 points where it's easy to identify the x and y, and then do change in y over change in x for the gradient. Okay, so the rate in this case is equal to the gradient, which is the same as change in y over change in x. Okay, if a reaction is going faster, then it will have a steeper gradient, but still finish at the same maximum amount of product. If the reaction is going slower, the gradient will be less steep, but still finish at the same maximum amount of product made. Okay, sometimes in questions you're required to sketch a faster or a slower reaction. This one would be faster. This one would be slower. So in line with this being faster, how can we actually increase the rate of reaction? Let's go back to basics. Why does a reaction happen in the first place? It happens because some atoms or molecules will collide with enough energy for that collision to be successful, thereby turning them into a product or products. Okay? The collisions between particles have to be successful. They have to collide with enough energy to then bonds be broken, bonds be made. That energy has to be there for the reaction. Each particle colliding with another particle, if it doesn't have enough energy, it won't turn into a product. What we need to do is increase the chances of the collisions between the particles being successful if we want to make the reaction faster. And we can do that in 4 ways. We can increase the temperature. When we increase the temperature, what we are doing is increasing the energy with which particles can move. So when we increase temperature, we increase the kinetic energy of our particles, of our reactant particles, making them move faster, making it more likely that they're going to collide with enough energy to be successful, for that collision to be successful. What we're doing is we're increasing the frequency of, not collisions, but successful collisions. By increasing the kinetic energy, we do that by increasing the temperature. That's one of the ways to increase the rate of reaction. Another way to increase the rate of reaction is to increase the concentration of particles or the pressure that the particles are within. Okay. Now, when we increase the concentration, we make the particles, we make the number of particles in a given space greater. Okay. So we make sure that there's more particles in a given volume, space. So if there are more particles in a given volume or a given space, there's a higher frequency of successful collisions, and the rate of reaction can be increased. The third way, we can increase the surface area. When we increase the surface area, the pieces that we are using become smaller. Okay, the pieces become smaller. So we could turn one of the reactants into like a fine powder, make the pieces smaller, increase the surface area. Increasing the surface area to volume ratio. What that means, I'll lay it out like this. Say if we had a piece like this, and that could be quite a large piece of one of our reactants. If we make it smaller, rather than just having these surfaces available to collide with another reactant, we've now created all of the surfaces when we've made the piece smaller. So we've increased the surface area, okay? Which means more of the particles are available to react. If more particles are available to react, there's a higher frequency of successful collisions, okay? The fourth way to increase the rate of a reaction is to use a catalyst. Now, what a catalyst does is it speeds up a reaction, but it doesn't take part in it. Okay, and to help us with this, I'm going to refer back to energy profile diagrams, where we have our reactants and our products. And we have energy here, and we have the rate of reaction here, or the progress of the reaction, so how it's happening over time. And this could be a measure of the energy needed, the activation energy needed for that reaction. And that will be like a set value. If we add a catalyst, what we're doing is we're lowering the activation energy. So with a catalyst, we would be like this. And the activation energy would be a lot less. So this one is with a catalyst. So by using a catalyst, what we're doing is lowering the activation energy, the EA. And by doing that, less energy is needed, okay, for the reaction to happen. Therefore, the reaction is more likely to happen, or we're going to get more reaction for a lower temperature, okay, thereby increasing the frequency of successful collisions. Each of these ways would make our rate of reaction quicker.